Testing. 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 All right. Works, and we are live. Welcome to another Hoopo video. Today we're going to be doing a bit of paper reading. We're looking at a paper called Segment Anything. This is a paper coming out of Meta AI Research, formerly known as Facebook AI Research, or FAIR. You got a couple heavy hitters here. You got Ross Gershik, guy, a lot of computer vision stuff for a while. And pretty cool little thing. So we see here, this is the demo for it. This is basically a large segmentation model that has been pre-trained on a huge amount of data for a very long time, right? The type of research that only the big AI companies can do. But see here how Zero Shot can kind of segment anything. So still make some mistakes. For example, here you have kind of the head of one cat and the head of another cat, and you're getting double mask there. But you know, for the most part, it's actually quite good. It detects these cats separately, put on this head. There is a GitHub for this. Seems mostly fine. The dependencies are pretty standard, no crazy stuff going on here. I don't like that it uses PyCoco tools, but I think the big data set that they're using is in the Coco format, hence the PyCoco. I just think that PyCoco tool is kind of a trash module. ONNX runtime and ONNX here. This is the open neural net exchange format. So the reason have these is so that you can take this model, which is obviously because it comes out of Facebook, it's probably implemented in PyTorch. This will allow you to use it in TensorFlow or whatever other deep learning framework you want that is supported by that. They do have some checkpoints. I did download them. They're basically a couple gigs. I think this one's 2 gigs, then you have 1 gig, and then you have like a 500 megabyte one. So you have a couple different sizes of the model. Yeah, excited to see what the hype is about. So let's get to it. We got figure 1. We aim to build a foundation model for segmentation. Okay, so foundation models are terminology that I think Stanford came up with, but basically the idea of a foundation model is a very large model that has been trained on a very large data set with a relatively generic task, such as filling in masks, next word prediction, or next token prediction, things like that. Kind of these generic self-supervised tasks usually. And then you create this very large model, and then the point is that you can take this model, which is called the foundation model, and you can fine-tune it for a downstream task. So in a way, the model acts as a foundation for future models, right? And foundation model for segmentation seems perhaps a little bit weird, because to me segmentation is already specific enough that why would there be a foundation model for segmentation? But let's see, really the foundation model would be this part here, the image encoder, and then the mask decoder and prompt encoder would be the segmentation. Introducing 3 interconnected components: a promptable segmentation task, a segmentation model, and a data engine collecting our data set of over 1 billion masks. So a whole lot of data. Sure. Okay. We introduced the Segment Anything project, a new task, model, and dataset for image segmentation. Using our efficient model in a data collection loop, built the largest segmentation set today. So over 1 billion masks on 11 million licensed privacy respecting images. This to me is really the biggest appeal of this image, that this is probably the largest amount of data that any segmentation model has been trained on. The model is designed and trained to be promptable so it can transfer zero shot to new image tasks. We evaluate its capabilities on numerous tasks and find that its zero shot performance is impressive, often competitive with or even superior to prior fully supervised results. So kind of going with the theme, the power laws in machine learning are real, and you're going to get better results with these huge data sets than you are fully supervised smaller data sets, right? So people have been training segmentation models on Cocoa and other smaller data sets for years, and obviously there's been improvements in techniques, but really, if you want to push state of the art, you're going to have to do it with a huge data set, and that's exactly what they did in this. We're releasing the Segment Anything model and a corresponding data set of 1 billion masks to foster research. Good. Hopefully, this kind of feels like it replaces Cocoa, so maybe we're approaching the end of Cocoa. Even though realistically, like, who the hell is going to be able to train on this, right? You're going to need a whole lot of A100s to train on this. Large language models pre-trained on web-scale datasets are revolutionizing NLP. These foundation models can generalize to tasks beyond those seen during training. Yeah, I think the generalized to tasks and data distributions within reason, right? Because I'm pretty sure if I took this segmentation model and applied it to the scroll prize, for example, that we've been looking at, it's not going to work because the distribution is too different. Capability is often implemented with prompt engineering, handcrafted text. When scaled and trained with abundant text corpora, these models, Zero and FewShot, compare surprisingly well. The fine-tuning models, I wonder if they're using clip. Oh, there you go. There's a clip mention. Empirical trends show this behavior improving with model scale, dataset size, and total training. So, confirming the scaling laws that everybody knows at this point. Foundation models have been explored in computer vision, albeit to a lesser extent. The most prominent illustration align text and images, clip and align, and blip. Well, I think those are really the true foundation models in computer vision, especially because they're used so prominently and consistently. Once trained, engineering text prompts enable zero-shot generalization to novel visual concepts. Such encoders also compose effectively with other modules to enable downstream tasks, such as image generation. For many, abundant training data does not exist. I think it depends on what you want to do. I think if you use a self-supervised task, such as reconstructing, filling in masks, so the same way that you can take a sentence and then blank out a token and then ask the model to basically recreate that token, you can do the same thing with images. You can take an image, you can cut out a chunk of it, and then you can ask the model to generate the chunk that is missing, and then that's basically an infinite self-supervised task where you can take every single image and just do this: take a chunk out, generate the chunk, take a chunk out, generate the chunk. So I think what they really meant to say is that training data specifically for the task of segmentation has been limited so far to things like Cocoa, and this is order of magnitude more than that. Seek to develop a promptable model and pre-train it on a broad data set using a task that enables powerful generalization. Okay, so hopefully maybe we see some arguments as to why segmentation is the best task to do this. task model and data, we address the following questions. What task will enable zero-shot generalization? What is the corresponding model architecture? And what data can power this task? Okay, so they haven't really mentioned model architecture yet, but that should be interesting. I suspect it'll be a vision transformer. These questions are entangled and require comprehensive solution. We start by defining a promptable segmentation task that is general enough to provide a powerful objective. Promptable segmentation task. So maybe they're changing the exact nature of segmentation and how they're training that. Task requires a model that supports flexible prompting. You need diverse, large-scale source of data. There's no web-scale application. Build a data engine. Iterate between using our efficient model to assist in collection and using. Okay, so this is a little bit telling you. And this in a form is a way of self-supervised learning, right? You're basically, sometimes this is called like pseudo-labeling, where you use one model to create a labeled data set, and then you use that labeled data set in a supervised learning fashion to train the same model, and then you kind of basically just repeat it in a circle, right? In this cycle, like use the model to label the images, use the images to train the model, rinse, repeat. We introduce each interconnected component next, followed by the data set we created and the that demonstrate the effectiveness of our approach. Foundation models are promising development. Propose the promptable segmentation task. Goal is to return a valid segmentation task given. Simply specifies what to segment spatial text. This is the important part here. In this demo, right, what I'm providing here with my mouse is spatial. So you could, when they say prompt, they're saying segment out the cat, right? It would be text, and they would convert that text into some kind of visual token with something like clip. But spatial means that it's the position of some point in the image, and then it's almost finding everything related to that. So that actually seems like the more interesting modification to the segmentation problem is the spatial aspect. Spatial information being used as the prompt. Even when a prompt is ambiguous, could refer to multiple objects. The object output should be a reasonable mask for at least one of those objects. Use the promptable segmentation mask as both a pre-training objective and solve general downstream. Okay. The promptable segmentation task and the real world use impose constraints. In particular, the model must support flexible prompts. Needs to compute masks in amortized real time. Okay, then what does this amortized word mean? Right? They said real time and now they're calling it amortized real time, so starting to go back on what they were saying here. Found that a simple design satisfies all three constraints. You have three parts here. You have a powerful image encoder, embedding. You have a prompt encoder that embeds the prompt. This is basically just natural language tokenizer. Like both of these here, you would probably want to use clip, but given that clip is almost probably weaker than the model that they have here, they probably trained a new version of clip themselves. And the two information sources are combined in a lightweight mask decoder. We refer to this model as segment anything model. So the three parts of here. So the model itself, there's three different parts. There's the mask decoder, the image encoder, and then the prompt decoder. Given an image embedding the prompt encoder and mask decoder predict a mask in around 50 milliseconds in a web browser. I don't think the model's running in a web browser. I think the model's probably running on some backend. Makes SAM ambiguity aware. We designed it to predict multiple masks from a single prompt, allowing SAM to naturally. Okay, so they're doing a little bit of like a top 5, top 1 kind of situation where they don't just have one prediction, they'll have probably a dozen predictions, and then they'll have some additional refining process that selects the best prediction from that. Data engine. To strong generalization, we found it necessary to train SAM on a large and diverse set of masks beyond any segmentation dataset that already exists. While a typical approach for foundation models is to obtain data online, masks are not naturally abundant and thus an alternative strategy. Yeah, masks are not naturally abundant because they're kind of artificial, you know? And you would think that maybe as AI progresses, we would move away from bounding boxes and segmentation masks, right, which were really the product of the supervised learning era. And you would think we would move away from that, but still clinging on. You know, people are still making bounding box detection models and mask segmentation models. Solutions to build a data engine. Data engine has 3 stages: assisted, manual, semi-automatic, and fully automatic. First stage, SAM assists annotators in annotating masks, similar to a classic interactive segmentation setup. So this is, if you guys have ever heard of like segmentation, kind of like a Mechanical Turk, right? So basically there's these companies, kind of like Scale AI, where you pay and you'll have these people, usually in third world countries, who sit there and annotate images. And years ago, they used to like actually draw boxes. So they would get an image like this and they would sit here and they would like basically trace out each of these cats. But nowadays, the way that they do these manual segmentations is they usually have kind of these interactive segmentation tools where the manual annotators are kind of like doing something similar to this, where they're kind of like already getting a partial result, but then what they would do is then they correct it. So already you're seeing segmentation and detection and any kind of labeling task is already partially assisted by models. And this is basically just a step beyond that. SAM can automatically generate masks for a subset of objects by prompting it with likely object locations. Objects. We prompt SAM with a regular grid of foreground points, yielding on average 100 high-quality masks per image. So that is this everything here in the demo. So you see how it creates basically all these points, and then it samples the masks at each of those points, and then does some kind of NMS equivalent, right, non-max suppression, and then you get masks for everything. So that is basically the spatial information being used as a way to get all the masks automatically. Final dataset, SA1B, includes more than 1 billion masks, 11 million licensed and privacy-preserving images. Collected fully automatically using the final stage of our data engine, has 400 times more masks than any existing segmentation dataset. Verify extensively, the masks are of high quality and diversity. Hope SAB1 becomes a valuable resource for aiming to build new foundation models. Study the report on potential fairness concerns and biases. Similarly across different people. Okay, responsible AI section here. experiments. Using a diverse new suite of 23 segmentation datasets, we find that SAM produces high-quality masks from a single background point. Now, this is spatial prompting. Find a consistent, strong, quantitative and qualitative results in a variety of downstream tasks using zero-shot transfer protocol using prompt engineering, including edge detection, object proposal generation, segmentation, and a preliminary exploration of text task prediction. Okay, so these are slightly different computer vision tasks here. You have edge detection, you have object proposal, instance segmentation, which is different from semantic segmentation. There's slightly different types of segmentation tasks, so they probably just benchmark on all the different computer vision tasks. Releasing and making it available under Apache 2 license. Perfect. All right, we got some images here. So some of the things to look at here is the relative size of things. So you see how here you have one object category is this grass, and that is a very large segmentation mask. And then in the same image, you have a segmentation mask for a little bush in the background. So this is something in segmentation that's always been an issue before, and even in object detection too, where being able to detect small objects simultaneously with the kind of objects that are big, and not like big and small in the sense of the real world, but big and small in the sense of how much of the image do they take up. So I like to see that. Another thing I'm seeing is just the number of things here. So in this picture here with the soup, or this one here with the orange, is just like the raw number of objects that are individually segmented. That's also relative. That's also impressive. So the different sizes is impressive. The fact that there's a huge amount of objects is also impressive. And I guess the cleanliness is impressive too. Like at these umbrellas, just how clean a lot of these masks are. Very impressive. But there's still some mistakes here. Like for example, you see here on these tunas, the like kind of tail end of the tuna that has been cut is seen as a separate thing from the body of the tuna. Sometimes the fins are seen separately. Here with this person, right, the part of their t-shirt sticking out is separate from the main body, versus I feel like the whole person should be segmented. Are you thinking this will work on the Herculean scrolls? I think that it's not going to work off the bat, right? Because the scrolls are just a really weird data format. It's like an X-ray, it looks like noise. It's not a natural image. But I think that if we know anything from deep learning is that scale just trumps everything. So the fact that this is the biggest segmentation model ever, right? It's like just bigger than anything that's ever been created, right? I think there's just more signal there. So I think if someone can figure out how to take this and fine-tune it, or not fine-tune it, but basically adapt it to the task of kind of ink classification, I think you could see there could be something there, right? Because I, for example, like a lot of people are using pre-trained models for the Herculean scrolls, and those pre-trained models are based around ImageNet, right? Which ImageNet is significantly smaller than this data set that they used, right? Like ImageNet size, I think it's 14 million images, but that's not even the one. ImageNet 1K, one that I'm thinking of. ImageNet 1K is 1.2 million images, right? This is 10 times that, right? 11 million images with over 1 billion masks. So I don't know. It's not specifically the task of classification. It's not the same. It's almost like a different imaging modality, right? This is RGB images. The scrolls are these slices of an X-ray. So it's almost like a different imaging modality, but I feel like people are underestimating just how powerful pre-trained models are, and it could actually be the best result. And the fact that it's Apache licensed, right? Apache 2.0, you can use it here. The GitHub looks pretty good. I think to me I'm definitely excited. I'm definitely potentially going to try it, but we'll see if I have time. All right, let's get into the actual meat of this. We take inspiration from NLP, natural language processing, which is basically just text, where the next token prediction task is used for foundation model pre-training. Yeah, so generally foundation models are such a huge amount of data that you're never really going to be able to label it. So the way that they train foundation models is with some kind of self-supervised task, right? Which is next token prediction, filling in mask, something like that. To build a foundation, we aim to define a task with analogous capabilities. Start by translating the idea of a prompt to segmentation, where the prompt can be a set of foreground or background points, rough box or mask, freeform text, or any information indicating what to segment in an image. This is like kind of very different, right? Because to me, a point is very different from a text. I guess they're just changing it all into embeddings. But these are very different types of tasks to me. Requirement of a valid mask simply means that even when the prompt is ambiguous, the output should return a reasonable mask. Choose this task because it leads to a natural pre-training algorithm and a general method for zero-shot transfer. The promptable segmentation task suggests a natural pre-training algorithm that simulates a sequence of prompts for each training sample and compares the model's mask against the ground truth. Yeah, this is the problem here. It's like what is the ground truth, right? Like these masks aren't actually ground truth. They're like pseudo ground truth. We adapt this method for interactive segmentation, although unlike interactive segmentation, whose aim is to predict a valid mask, our aim is to always predict a valid mask for any prompt. It ensures that our pre-trained model is effective in use cases that involve ambiguity. Specialized modeling training loss choice. Okay, are they going to explain it? Is this going to be an OpenAI paper where they just don't even explain anything? I don't see any math. It's not looking good. Maybe this ends up being a whole nothing burger and they never explain anything. It looks like they're kind of explaining things though. Look at this, they got some plots, so okay. Let's not lose hope. Maybe they do actually explain. Okay. Training task endows the model with the ability to respond appropriately to any prompt, and thus downstream tasks can be solved by engineering appropriate prompts. I fine-tune it though. One has a bounding box detector for cats. Cat instance segmentation can be solved by providing the detector's box output as a prompt to our model. Oh, okay, I see. This is interesting to me. It seems like kind of what they're suggesting here is that the way they want to do the zero-shot transfer, right, this is backwards, right? Normally the zero-shot transfer is I don't have any detection model. I want to train a detection model. I use the foundation model and I train an additional head on top of the foundation model, or I fine-tune the foundation model to my task. But in the way that they're describing the zero-shot transfer here, you already have a detection model. The detection model gives you a bounding box, and then you feed that bounding box as the input to this segmentation model, and it'll segment it out. I don't know if I'd call that zero-shot. That's just like, this is almost like a different thing here. Segmentation is a broad field. There is interactive segmentation, superpixelation, object proposal generation, foreground segmentation, semantic segmentation, instance segmentation, panoptic segmentation. Yeah, there's all these different types of segmentation. So, for example, the difference between instance segmentation and semantic segmentation is if you're doing instance segmentation, you want to detect each of these cats individually, but if you were doing semantic segmentation, every single one of these cats would be the same. It would just be the category cat. So sometimes you want to basically do classification at the pixel level. Sometimes you want to separate out the individual cats. You want to write, for example, in instance segmentation, you would want this part here, which is the head of the cat, and this part here, which is kind of the body of the cat. You would want this to be the same mask. You would actually want the model to say, okay, well, this part here of this cat and this part here of this cat are the same cat, right? And there's papers where they take special care to do that, right? Where basically you can cut part of the giraffe can be hidden, and it knows that the front of the giraffe and the back of the giraffe correspond to the same giraffe. So there's a lot of different types of segmentation, and I mean, they're all kind of the same, right? Segmentation is object detection if you kind of blur your eyes enough, but there is a bunch of different kind of subtypes of segmentation. New segmentation tasks. Lost our place. There we go. In a multitask, a single model performs a fixed set of tasks, but then the training and test tasks are the same. An important distinction in our work is that the model trained for promptable segmentation can perform a new different task by acting as a component in a larger system. Yeah, but to me, this is still just kind of, you're playing with words here, right? Because it's like, they're saying, okay, well, most models are task specific, and ours is a foundation model that is task agnostic and will work for a variety of tasks. And it's like, okay, well, what kind of task does it work on? It works on all these different variants of segmentation. So is this really a generic foundation model, or is this just a segmentation model, right? There's nothing, because if you try to do anything else other than segmentation with this, it might not work very well, right? So this is a very specialized model too. It's also very task specific. It's specific to the task of segmentation. Prompting and composition are powerful tools that enable single models to be used in sensible ways, potentially to accomplish tasks unknown at the time of model design. This approach is analogous to how other foundation models are used, e.g. how CLIP, text image alignment component of DALL-E. Yeah, CLIP, probably the best computer vision model in the world right now. Extremely popular, and it's basically it's what allows you to take texts and images and deal with them in a joint way, right? So CLIP will basically take a text and project it into some embedding space, and it can also take images and project it into that same embedding space. So you can say, how similar is this image to this image? What are the images that most similarly correspond with this text? How similar is this text to this text? So it's a much more task agnostic model, right? Because anything involving texts and images, you can use CLIP, versus this model here, SAM, the one in this paper, much less task agnostic than CLIP. So I'm very comfortable calling CLIP a foundation model. I'm a lot less comfortable calling this SAM a foundation model. We anticipate. Dave Jackson, thanks for doing these streams. Appreciate it. Thanks, man. Hope you like it. I know sometimes these streams can be kind of boring. I don't understand how to make things entertaining. You know, I'm just here to read the paper, and people want it. People want it. I think the best way to actually consume my content is to actually either ask questions live. So if you guys have questions, obviously the live, you can ask them to me and I'll answer. But if you're just watching these videos, actually, I think the best thing to do is 2x speed. Like, put me on 2x speed and just blast through the whole paper. Kind of once you start listening to things at like faster speed, like 2x, it's good. Whole game changer when it comes to learning. Wide variety of applications, trained specifically for a set of tasks. Also interesting to compare promptable and interactive segmentation through the lens of composition. While interactive segmentation models are designed with human users in mind, model trained for promptable segmentation can also be composed into a larger algorithmic system. Yeah, so they're also kind of setting up, right? We now live in a post-GPT world, and if you guys know what Toolformer is, right? Toolformer is this probably one of the best papers in a while, but Toolformer is this concept that you can basically get large language models to use tools, and specifically the tools that they're using can be models like this, right? Can be this type of segmentation model. So really, when I see this segment anything by Facebook here, I bet you that their own internal LLM is going to be using this segmentation model when you ask it to do any kind of segmentation task. So really, in a Toolformer world, being the best segmentation model actually is quite important and quite valuable. So it makes sense that Facebook would try to do that, because they also probably have the best image data set available, right? They have every single Facebook picture that people took since the beginning of time. They have Instagram. They have so much image data that I feel like Facebook is always going to be the kind of the best segmentation detection models are going to come out of this company, because they just have better data than anybody else, and they also have a shit ton of money, so they can train for a very long time. Okay, now we have figure 4 here, segment anything model. Take an image, you feed it through this image encoder, then you get your image embedding. The fact that these are little squares, again, to me, just makes me think that they're going to tell us that this is a vision transformer. Then you get the mask. The mask goes through a convnet that gets somehow concatenated with the image embedding. Maybe it, I would think it would mask out specific parts of the image embedding. I don't know why they're feeding it through a convnet here. Then you have your prompt encoder here, which takes in either points or box or text. So again, the points is basically you can click on something, right? And that'll be like a specific point, like basically a location within the image. A box is going to be like a bounding box, so basically a corner and then a height and a width. And then a text, which is probably already tokenized. And then that goes into their mask decoder, and then their mask decoder proposes a variety of masks with a score for each one. SAM can output multiple valid masks and associated confidence scores. Okay, has the image encoder, prompt encoder, and the mask decoder. Okay. We describe these components at a high level. Why not tell me the low level? Fuck the fact that people don't want to tell you. Like, tell me. I don't like this. I don't like where AI research is going, where everybody's just keeping things secret. Okay, so it is a vision transformer. Minimally adapted. So minimally adapted probably means that they haven't really done a ton of things, or that the things that they've done they don't want to tell you about. Image encoder runs once per image. It can be applied prior to prompting the model. Yeah, the image encoder is probably the largest model here out of all of these, and it's going to be the one that takes the longest amount of time to perform inference, and it's also going to be the one that takes the most memory, right? So this image encoder, very unlikely that you can even fit it on your consumer GPU, at least the big version of it. Consider two sets of prompts, sparse and dense. We represent points in boxes by positional encodings. Okay, so they're using positional encodings for the points in boxes. So go back to our demo, right? If you have, so the point that you're giving it is where my mouse is, right? And that is going to be positionally encoded. So what does that mean? It means that this point, you're not just going to say, okay, it's about 0.5, 0.5, right? You're going to use some kind of cosine or sine, some kind of fancy position encoding that is a little bit more rich in information and signal than just exact pixel location. Sloppy today. Get back up here. Get back up here. Dense prompts are embedded using convolution. This I don't understand. Why are they taking the mask and embedding the mask with a convolution? I would have thought that they take the mask, they use it to mask out the parts of the image embedding that aren't relevant. Summed element-wise with... That's also weird. So, yeah, intuitively I would have thought they would have taken this mask and they would have used it to mask out this part of the image embedding, but they're actually taking the mask, feeding it through a convnet, and then literally summing these two vectors, the image embedding and then the weird mask embedding. So that's a little bit unusual. The mask decoder efficiently maps the embedding, prompt embedding, in an output token to mask. This design employs a modification of a transformer decoder block, followed by a dynamic mask prediction head. Modified decoder block uses prompt self-attention and cross-attention. Okay. Different types of attention mechanism here. Update all embeddings. After running two blocks, we upsample the image embedding and an MLP maps. Upsample the image embedding. Okay, so it's doing it at a lower resolution, right? Be faster. They want this to run real time. Then they have just a generic multi-layer perceptron, which maps the output token to a dynamic linear classifier, which then computes the mask foreground probability. So then they finally have some classifier, and then the classifier basically classifies things as either foreground or background. Binary classification. With one output, the model will average multiple valid masks. To address this, we modify the model to predict multiple output masks for a single prompt. Found 3 mask outputs is sufficient to address most common cases. During training, we backprop only the minimum loss over masks. To rank masks, we model predicts a confidence score, estimated IOU for mask. This is intersection over union, so maybe they're doing some kind of NMS type equivalent thing, right? Where they say, okay, well, this mask and this mask and this mask, like, what is the overlap between all 3 of the predicted masks? There's probably even more than 3 predictions. And using that along with the scores, you can probably find the kind of average mask, or like the combined mask. Given a pre-computed image embedding, the prompt encoder and mask decoder on a CPU, 50 milliseconds. So basically this image encoder is the heaviest part, and that's going to run separately. And this part here, the mask decoder and the prompt encoder, these are the parts of the model that they want to run really, really quickly. So these are going to be designed with the primary kind of objective being make this as fast as possible, and this is going to be designed with make it as powerful as possible, right? So this is the part that they're really trying to cram as much information in it by training it on the biggest possible data set for the longest amount of time. And then this part here, they just want it to run as fast as possible, so they're going to try to make it as tiny as possible. Supervised mask prediction with the linear combination of focal loss and dice loss. So these are 2 different types of losses. Trained for the prompt segmentation task using a mixture of geometric prompts. What is geometric prompts? And simulate an interactive setup by randomly sampling prompts in 11 rounds per masks. What is this? Randomly sampling prompts. Okay, so they're doing some kind of fancy prompt. This isn't prompt engineering, right? But it's like they're training this in a self-supervised way, right? Where it's very easy to take to say, okay, well, I'm going to pick a random spot in the image, and that's going to be my spatial input, and I'm going to say, okay, well, what is the segmentation resulting from this, right? But if your prompts are text, how do you get prompts that are text for sufficient or anything, right? I suspect that they're probably going to use clip, right? They probably feed this entire image into clip or something like blip, right? Like an image captioning model. And then clip will say, okay, bears, river, Alaska, summer, sunlight. And then they'll design some prompts that are based around that. They'll say, okay, well, bear, segment out bear. And that'll basically allow them to do that. So that's my guess as to what they mean here by these randomly sampled prompts, but I don't know, maybe I should stop making guesses and just keep reading so we can actually get to it. Data engine is 3 stages: model-assisted manual annotation stage, semi-automatic stage, and then fully automatic stage. So here this is basically supervised learning and semi-supervised learning, and then at this point self-supervised learning. So I like how they go kind of, they ramp it up, right? That's kind of thing. Resembling classic interactive segmentation, a team of professional annotators. Professional annotators. Wonder who has that on their LinkedIn. I think the people who are professional annotators don't have LinkedIn. Malik, are they randomly sampling different crops of the image? They probably do have augmentation. So very common type of data augmentation when you're doing image and computer vision tasks is to basically randomly crop parts of the image. I don't know if they'll say exactly what they do, but here, data augmentation. Data augmentation may be useful. Large-scale jitter. We follow the suggested default strategies for data preprocessing, i.e. data augmentation, and do not change any parameters. Okay, so they don't say exactly that they use random crops, but I bet you they're using random crops. It's pretty standard, and it'd be a no-brainer for them to do so. Masks could be refined using pixel-precise brush and eraser tools. So this is really what professional annotators, what they did 10 years ago is different from what they do now. Like what they did 10 years ago is like they would like literally sit here and trace out every single bear, and it was absolutely brutal work. But nowadays what they're doing is they're using these kind of like pseudo labeled, and then they just like fix the prompt. So for example here you see how like when I select this little young bear, it still gets the paw for this big bear, right? You see how this paw here, this paw should be separate from this little bear. So that's something that the annotator would do, is they would basically fix the fact that this mask here includes parts of a different bear. I mean, for the bounding box prompts. Yeah, I don't know. I don't know what we don't know yet. Malik, let's keep reading, because I'm thinking they're gonna explain it to us, and then we'll know. We did not impose semantic constraints for labeling objects, and annotators freely labeled both stuff and things. We suggested annotators label objects they could name or describe, but did not collect these names or descriptions. Annotators were asked to label objects in order of prominence. What the fuck does that even mean? And encouraged to proceed to the next image once a mask took over 30 seconds. Okay. So they're only really spending 30 seconds per image. SAM was trained using common public segmentation datasets. After sufficient data annotation, SAM was retrained using only newly annotated masks. Huh. Okay, this is interesting. So they trained SAM on common segmentation datasets, which is, I think, just Cocoa. And then once they trained it on Cocoa, they use it to label their big data set, right? Their 11 million image data set. And then they train on that data set to get the final model. So I love this kind of like layering, right? I love this idea of like training a model and then the model generates its own data to train the model again, right? This kind of like improving the model by using the model. I think that you could do that for, this is somewhat analogous to, for example, Alpaca and Llama, right? With Alpaca is a text model that was trained by fine-tuning a Llama model on a data set that was generated by a GPT model. So I think this concept of using models to basically create their own data sets or create data sets for different models, I think that trend, you're going to see it just more and more and more. And maybe that'll be the real use case of this type of foundation model in computer vision, is actually just data set generation. As more masks were collected, the image encoder is scaled from VITB to VITH. So these are vision transformers. These are different sizes. The VITH is a bigger one. I think VITB is smaller. So actually, you guys think that chat this? How much bigger is VITH, VITB? I don't have the exact numbers for these specific models. I can provide a general comparison based on the original VIT paper. I don't think the Vision Transformer paper wasn't Google, right? I'm pretty sure that was Facebook. VIT. It's actually Google? Oh, yeah. I guess it was. Okay, never mind. VIT base, VITH. H stands for huge. So it's VIT base and VIT huge. Average annotation time decreased from 34 to 14 seconds as the model improved. We note that 14 seconds is 6.5 times faster than mask annotation for Cocoa and only 2 times slower than bounding box label. As SAM improved, the average number of masks per image increased from 22 to 44. Yeah, I think this is kind of what I was saying. It's like one of the most impressive things to me is just how many masks, right? Like, just look at the just number of objects in this scene. Very impressive. In total, we retrained our model 6 times, so it went through this loop of creating its own data set about 6 times. At this stage, we aim to increase the diversity of masks in order to improve our model's ability to segment everything. Diversity of masks. Focus annotators on less prominent objects. We first automatically detected confident masks. Then we presented annotators with pre-filled images and annotate any additional objects. Collected an additional 5.9 million masks. Periodically retrained our model on newly collected data. Average annotation time per mask went back up to 34 seconds, and these objects were more challenging to Average number of masks went from 44 to 70 masks. Yeah, so they're basically, as they're training their model more and more, right? So they start with just basically a Cocoa segmentation model trained on Cocoa. Then they use that to segment more stuff, right? And then more stuff. So you can see here how every time they generate or they use the model to generate the masks, they increase the number of masks, more resolution, get everything in there, right? Because something like Cocoa, Cocoa Dataset, right? Not everything is segmented, right? Like, for example, here in these images, right? Just like compare this, right? Like, look at this. All you have is the dogs. All you have is a couple of the things here, right? Compare that to here, where literally basically everything in the image is segmented. So I think this is the big win to me. It's like if you need everything in the image segmented, this is going to be the way to go. Annotation was fully automatic, feasible due to do 2 major enhancements. We had collected enough masks to greatly improve the model. This stage had developed the ambiguity-aware model, which allowed us to predict valid masks even in ambiguous cases. We prompted the model with a 32 by 32 rectangular grid of points, and for each point predicted the set of masks. If a point lies on a part or subpart, our model will return the subpart, part, and whole object. Okay. IOU prediction of our model is used to select confident masks. We identified and selected only stable masks. Mask is stable if you have some kind of probability threshold for stability. There you go. There's the non-maximum suppression that we were guessing. NMS to filter duplicates. To further improve the quality of smaller masks, we also process multiple overlapping zoomed-in image crops. There you go. There's your answer, Malik. They have the image crops. For further details of this stage, we applied fully automatic mask generation to all 11 million images, producing a total of 1.1 billion high-quality masks. Image-sized, normalized mask center distributions. Okay, so this is different data sets. So obviously you have Cocoa here, and you have SA1B, which is this data set. And this is showing you the mask center distribution. So where in the image is the mask? And I'm not exactly sure if that's exactly what that means, but I've seen these type of diagrams before. And really what they're showing you is that much like there's kind of some distribution of pixels that is specific to a data set, and different data sets have different kind of pixel distributions, different appearance, there's also a distribution of like where the masks are and how big the masks are relative to the image itself. And part of what you're doing when you're doing kind of transfer learning and taking one model and trying to use it for a new task is that you're trying to get it to shift the distribution that it's good at, right? And like this is really a visual example of how the distribution of Cocoa is different from the distribution of ADE 20K, right? You can see how there's kind of this like strong line here. And I guess what they're trying to show you here is that SA1B, right? I would guess that you probably don't want this very strong dot in the middle. Ideally, the theoretical best distribution here would just be like the same color everywhere, which means that there's no bias towards a specific mask center. But we compare with the existing data sets and analyze mask quality and properties. We are releasing SA1B to aid in future development of foundation models. We note that SA1B will be released under favorable licenses. We licensed a new set of 11 million images. These images are high resolution. Yeah, that is definitely very high resolution. It's definitely not the 224 by 224 or even Coco here, right? So Coco itself is 480 by 640, so much lower resolution. Faces and vehicle license plates have been blurred. 99% of the masks are generated automatically. Quality of the automatic masks is centrally important. We compare them directly to professional annotations and look at how various mask properties compare. Our main conclusion, as borne out, is that our automatic masks are high quality and effective for training models. To estimate mask quality, we randomly sample 500 images and ask our professional annotators to improve the quality of all masks in the images. This procedure resulted in a pair of automatically predicted and professionally corrected masks. We compute the IOU between each pair and found that 94% of masks have a greater than 90%. Okay, so they're basically just comparing the masks that the model outputs with the masks that some expert humans have and doing some kind of IOU between them, right? Intersection. How much is the overlap? And of course, right, the reason they're talking about it is because the model can do just as well as the humans. Plot the spatial distribution of object centers in SA1B compared to the largest. Okay, so this is the object center. That's what this means. It means the center of the mask. Where is it in the image? So one thing to note from this is that a lot of times people will talk about the object-centric bias in images, and what they mean is that humans, when we take pictures of things, we pretty much almost always like center the object of interest in the picture, right? It's very rare to have a picture of an emu or something like this, right? Like this bird, and have it just be in the top corner and then like most of the image is grass, right? Pretty much anytime humans take pictures, there's kind of like an object-centric bias to it. And that's what you see here with these very strong dots right in the middle, is that this image distribution that they're using, right, it's still images coming from humans that took pictures of those images. So there's going to be that object-centric bias in there. Yeah, here you go. Common photographer biases are present in all data. Greater coverage of image corners, and the two most similarity distributed images have a more prominent center bias. 11 times more images, 400 times more masks, Image relative mask size. Square root of the mask area divided by image area. Our dataset has more masks per image, also tends to include a greater percentage of small and medium relative size masks, which is what we noticed, right? Is that you're seeing little things and big things. Demo again. Let's go to something that's like very busy. Like this one. Okay, let's do everything. So everything will lay out a bunch of grids, and then it'll basically find the segmentation for each of those little points and then segment it out. But yeah, look at this. The fact that you have something like this that's very tiny in the same as something that's like this background here that's very big. This is still pretty impressive. I like how it segmented out the cable here. That's pretty impressive. Since the shape complexity is correlated with the mask size, we control the dataset's mask size distribution by first performing stratified sampling from binned mask sizes. Cavity distribution for a mask is broadly similar to that of other datasets. Figure 6. Okay, so number of masks per image. So you have the orange is this data set, Cocoa is this brown one. So you can see how Cocoa and some of these older data sets like ADE, they have a lot of images with not a lot of masks and then very few images with a lot of masks, right? Versus this SA1B data set, the kind of center of the kind of probability right here, around 51 to 200 masks. So more masks per image. The masks are smaller, right? So this orange has the smallest segmentation mask size. And percentage of masks concavity. What exactly is the concavity? Mask concavity, 1 minus mask area divided by area of mask's convex hull. Okay, so basically it's the convex hull of the mask is like the actual here. Convex hull. So here you have the actual object, and then the convex hull would be basically that, right? So like you wrap around the edges, right? So I don't exactly know what mask concavity, like what do you actually want that to be, right? It's like, it seems like it's just kind of a metric for the sake of a metric. Like is lower mask concavity better? Is higher mask concavity better? I don't know. Since shape complexity is correlated with mask size. Okay, so maybe it's like some kind of proxy for the complexity of the mask. Right? Maybe they're kind of looking at, if you look at something like Cocoa, right, you get this kind of polygon type looking mask. So if you have the mask convexity of a Cocoa mask versus the max convexity of something like this, where you have kind of very fine resolution, maybe that tells you just how detailed the mask is. So maybe this concavity metric is a proxy for the detail of the mask. Estimated geographic distribution. So this is more about kind of like fairness and bias, right? And basically they want to make sure that the images that they're using aren't just all coming from the US, because if they were all coming from the US, they'd be racist. So they want to make sure that the images are from all over the world. That's what they're showing you here. But no one cares about Antarctica or Greenland. This is kind of weird. 50 most common countries. The top country is Russia. What? Russia and Thailand? That's fucking weird. So basically, this segmentation model has been trained on mostly Russian images. Russian and Thailand images. Probably just because there's no data privacy laws in Russia, so they just downloaded the Facebook Russian dataset and no one can complain. Next, perform a responsible AI analysis. Blah, blah, blah. Substantially higher percentages of image in Europe and Asia. Got African images. Perceived gender representation, perceived skin tone, perceived age group. Fairness in segmenting people. If your data set is more diverse, it's going to be better at detecting dark versus light skin tones. I think this was more of a thing in the past. I think kind of maybe 5-6 years ago, like there was issues where computer vision models would not perform well with dark skin tones and they would perform better with light skin tones, and a lot of people didn't like that. But I think nowadays the models are a lot more powerful. There's a lot more data. The data is better distributed across all different types of geographies and ethnicity. So I think we're moving away from that, which is All right, zero-shot transfer experiments. We present zero-shot transfer experiments of the segment any model. We consider 5 tasks, 4 of which differ significantly from the promptable segmentation task. All right, we'll see what differ significantly means, because if there are just 4 types of segmentation task, I'm going to be annoyed. Datasets include novel image distributions, such as underwater or egocentric images, to our knowledge that do not appear in B. I wonder if it works for Herculean scrolls. Testing the core goal, introducing a valid mask from a single prompt. Sequence of experiments that traverse low, mid, and high level image understanding, roughly parallel the historical development of the field. Okay, so this is kind of cool. Is they're basically going to feed it incrementally harder tasks that roughly parallel the historical development of the field. So maybe they try MNIST, and then they try CFAR, and then they try ImageNet, and then they try COCO, and then finally they try SAM, or SA1B. We prompt SAM to perform edge detection, object proposal generation, instance segmentation, and then this kind of like text-based segmentation. So I don't know. So they like they say here, trained on how did I just like teleport down? Yeah, 4 significantly different tasks, but then the 4 significantly different tasks that they are talking about are edge detection, object detection, instance segmentation, and then differ significantly. I would argue that they do not. I think they're much the same. Pre-trained VIH image encoder that was trained on, say, one. For all other model and training details, refer to A. Zero-shot single-point validation mask. So for those of you that are in the kind of scroll prize community, this is the money right here. This is what you want from this paper, is this VITH image encoder that's been pre-trained. This thing is going to be badass, right? If you take this and just make sure that the input is correct and make sure that the output is correct, I think this might actually give you some really strong results on the scroll task. And it's available too. It's like down here. You can download it. They have the VITH model. Oh, yeah, this one here. Zero-shot, single-point, valid mask evaluation. Going to be a GIS and yeah, I'm not like, I actually haven't really ever done like a ton of like satellite imagery segmentation and stuff like that, but I know that it's actually a huge application area. Like there's a ton of money in like counting the number of cars in a parking lot, or seeing how much of a neighborhood has solar panels. Like a lot of cool stuff. I even saw an application where they use some kind of special type of satellite imagery, and they can detect where there's like kind of methane fumes coming out of the ground. So yeah, computer vision applied to satellite imagery is definitely huge. I'd love to learn more about that. Engineering with Beamer. If you have any like cool papers or cool GitHub repos about satellite imagery and how to deal with that, definitely post it on the Discord, because I think that's a huge application area. We evaluate segmenting an object from a single foreground point. The task is ill-posed, as one point can refer to multiple objects. Therefore, we supplement the standard mean IOU with a human study and watch. Okay, this is good. I like this. I like it when you use human subjective metrics rather than kind of these very precise mathematical quantifiable metrics. I actually think the qualitative metrics, where it's like you just ask a human, are better. By default, we sample points from the center of ground truth masks following the standard evaluation. Since SAM is capable of predicting multiple masks, we evaluate only the model's most confident mask. The model's most confident mask. We compare mainly to RITM, so a strong interactive segmenter that performs best on our benchmark. Use a newly compiled suite of 23 datasets with diverse image distributions. Similar here to the differ significantly in diverse image distributions. It's like, okay, well, how diverse is it? Are you using MRI images? Are you using like weird infrared images? Like, how diverse is your distribution really? Because I bet you it's probably just all iPhone pictures. This includes datasets for which SAM outperforms. Okay, so here's the actual 23 diverse stuff. So you have BBC. This actually looks relatively interesting. This is, I think, like a biology data set. So this is like a slide. So this is little bacteria. You have deep sea underwater images. You have egocentric images, right? So egocentric is like, for example, someone has like a camera on their forehead. If you're Facebook, it's really the Quest headsets, so like the VR headsets. You have heavy kind of fisheye lens. You have X-ray images. Okay, this is cool. This is like the X-ray at like the TSA. You have more egocentric, more egocentric. You have oil paintings. I don't know what doors is, but this looks like some kind of weird... That something very small, or is that like Jupiter? I don't know. You have cityscapes. Cityscapes is more autonomous vehicle, which is, in a sense, a type of egocentric dataset, but it's egocentric with respect to the autonomous vehicle, not a person. IBD, this is a satellite imagery dataset here. Okay, so maybe I gave them too much shit. Maybe this is a relatively diverse image distribution. You know, you do have a lot of different types of things here. I like how they have different modalities here too, right? They have the X-ray images. They have the these bio images. I don't know if X-ray and bio images are both one channel. Maybe they are. Here is the IOU delta at one center point. So I guess PPDLS is the one that it performs the worse on. Which one is PPDLS? This one here. Plants. So it does, I guess, the worse on plants and biology stuff. Yeah, so these data sets here, BBC, DOORS, PPDLS, these are the ones that it actually does the worst on, I'm guessing. Right, you don't, IOU, you don't want a delta, I would guess. The smaller the delta, the better. And then it performs the best on GTEA, which is egocentric. Yeah, that makes the most sense, because most of Facebook's images are going to be this kind of stuff here. Mask quality ratings by human annotators. Average mask rating, so again, they're rating them from 1 to 10. Obviously, it makes sense that the ground truth mask is going to be the cleanest. And then they're showing you that their model does the second best. Do you think the image encoder should be frozen or fine-tuning on your own data set? There's arguments for both, right? So if you don't freeze it, you're going to be pushing gradients into the model, and you have to be careful. So if you don't freeze the encoder and you have a very high learning rate, you're just going to like overwrite all the stuff that's in there, you know? Because you have to realize that these pre-trained models, they train them for very long and with like kind of a learning rate scheduling. So the last like 10 hours of training that pre-trained model has gotten has been at a very, very fine learning rate, right? At like a 0.000001, right? So if you take that and you suddenly start pushing gradients with like a 0.01 learning rate, you're kind of just overwriting all this training that they did at the end of that pre-trained model. With that said, sometimes the pre-trained model is a little bit different from your data set, right? So in the scroll prize, the Herculaneum, the scrolls themselves, the x-rays of the scrolls are so different from ImageNet that you could argue that you benefit from kind of letting some of the gradients flow through ImageNet, right? Flow through that pre-trained encoder. So I think the succinct answer to your question, Poison, is that if your data set distribution is very different from the data set distribution of the pre-trained model, don't freeze the encoder. Let the gradients flow, but be careful. If the dataset distribution is very similar to the dataset distribution of the pre-trained encoder, then do freeze the model. But that's just kind of like a general high-level understanding, and in reality, all of deep learning is kind of alchemy, and I've seen it happen both ways. I've seen freezing the training encoder working and not freezing the training encoder, or not freezing the image encoder working. One paper you should look at, if you're interested, is locked image tuning. So this paper, it's pretty good. We've actually read it on this channel as well, but they do these kind of experiments, right, where they basically they fine tune and they lock and they freeze certain parts of the thing and then not freeze certain parts of the thing, and then this is a slightly different thing because this is like image to text, so it's not exactly probably what you're talking about, but they talk about these concepts, right? This concept of like, when do you freeze it, how do you freeze it, and so on, right? So like training from scratch, fine tuning, locking certain parts. So I would recommend this paper if you're trying to think about whether or not you should freeze your encoder. Okay, where were we? Okay, we were here. Center points. Number of points. Random points. Okay, so MIOU. So what they're doing here, right, is that you give this model a point on the image, and then it'll segment based on that point in the image. So I guess what they're trying to say here is that you would want the number of points to not change the prediction, right? If I click here, I would want, like, if I click here and I click here and I click here, right, I should be getting the same mask every time, and the kind of the IOU for all of those masks should be pretty good. I think that's what they're trying to say here, right? And you can see here how comparing SAM, which is this paper, with Simple Click, which is like some other benchmark, if you only click once with Simple Click, you get a very bad MIOU, right? Which means that the masks aren't consistent. You're getting different answers depending on where you click. And what they're showing you here is that SAM, right, the model in this paper, even if you only click once, it actually still gives you a pretty good mask. The masks are still pretty consistent. So that's kind of my interpretation there, but mean IOU with varying number of points. SAM significantly outperforms prior interactive segmenters with 1 point and is on par with more points. Yeah, so this is kind of interesting where it's like you say this, but I don't want this. You know what I'm saying? Like you can say, I want this thing, but I do not want the edge. And there you go. Or let's do another image here. Yeah, this one will be. So I want this, but I want this frog, but I don't want the snail. There you go. Pretty good, right? All you need is 3 points, and then you got frog. Or let's say I want the reflection of the frog. So this, I don't want this part of the snail. Maybe can I do this too? Can I do just the frogs? Look at that. That's pretty good. Just the 2 frogs with maybe like 10 points. Okay. Look at automatic evaluation on the full suite of 23 dataset. Samuel's Heiser results on 16 of the 23. Full. Results on the human study. Error bars are 95% confidence intervals. A bladed, ambiguity-aware version of SAM with a single output mask has consistently lower ratings, although still higher than RITM. SAM's mean ratings fall between 7 and 9, which is the guideline. Okay, they compare to simple click and focal click. How old is simple click? Simple click is 2022. Damn, like imagine publishing a paper in 2022 and like literally within a year your paper is irrelevant because someone's already published a better one. That sucks. It's just, machine learning research is absolutely brutal. It moves so quickly that you just become outdated in a matter of fucking months. Achieve comparable results under either sampling method. This is the edge detection task. Of course, it makes sense that anything you do, segmentation models are going to be good at edge detection. We evaluate SAM on a classic low-level task of edge detection. Use a simplified version. We prompt SAM with 16 by 16 regular grid. Edge maps are computed using Sobel filtering. So this is basically, this is how they get from masks to the actual edges. So here, the way that edge detection is usually framed, it's like you want basically a version of the image, but with basically black pixels representing the edges and these white pixels representing not edge. So this is how they go from 768 predicted masks into a edge detected. We visualize representative edge maps. Observe that even though SAM was not trained, it produces reasonable edge maps. Recall at 50% precision is high. The cost of precision. Yeah, much like anything else in computer vision, you're trading off kind of recall and precision, right? There's this kind of, you can have very good recall, which means that you're kind of trigger happy, right? You're always detecting, but you never miss anything, right? Or you can have high precision where you're not trigger happy, you very rarely detect things, but when you detect them, they're guaranteed to be right, basically. So in some applications, you want high precision. Other applications, you want high recall. And performs well. HED. More classic edge detection method. Performs better than prior, though admittedly outdated. It's a very classy way of saying they're old, crusty. Mid-level task of object proposal generation. Standard average recall. Okay, so here you have mask average recall. You have the VITDH versus SAM. I think DET is also another Facebook model. DT Meta AI research called DEIT, right? Yeah. I don't know if this is exactly what they're referring to here. This might just be vision transformer huge trained for detection, but it might be this DEIT one. I mean, this seems kind of on par. It doesn't look like it's significantly worse or better. Maybe here on the rare ones. Okay. We focus on LVIS because it is a large number of categories. We compare a strong baseline implemented as a VIT-DET detector, the Cascade Mask RCNN VITH. We denote that this baseline corresponds to detector masquerading as proposal generation method that was shown to game average recall, making it a truly demanding comparison. Okay, so they're, I guess, saying that this thing that they're comparing it to, the VIT-DET, kind of overfit to this average recall metric. Maybe it's not a fair comparison, but oh, how much image was this VIT-DET trained on, right? SAM does remarkably well on several metrics. It outperforms on medium and large objects as well as rare and uncommon objects, or rare and common objects. Only underperforms on small objects and frequent objects. Okay, but part of it is it was literally trained on Elvis, so it's testing on the trained data set. Moving to higher level vision, we use SAM as the segmentation module of an instance segmenter. Segmentation is simple. We run an object detector and prompt SAM with its output boxes. So this is kind of how mask RCNN works. So kind of older, maybe not older, but a lot of segmentation models, the way they work is they first get kind of like a region of interest, right? Like a bounding box of the image, and then they segment that specific part of the image. So you guys have seen the mask RCNN paper. There's the picture with the cowboy that's pretty much ancient at this point, but if I can find it. Mask RCNN cowboy. Yeah, this one. So, see if I can find the original. Where's the original image? Either way, basically you're detecting a region of interest, and then that region of interest is the one that's actually getting a mask, right? So it makes the mask problem easier because the mask is a more consistent size, right? The way that you're training the masked part of your segmentation pipeline, it can make some stronger biases around the size of the mask relative to the image. Compare the mask predicted by SAM and VIT-DET, what I'm going to call it, on COCO. Looking at the mask AP metric, we observe gaps on both data sets where SAM is reasonably close, though certainly behind VIT-DET. We conducted an additional human study asking annotators zero-shot text to mask. Wait, this is what we want here. So this is COCO and then Elvis, and they're comparing it, same thing again, this VIT-DET to SAM. And yeah, I don't know, these numbers kind of look the same to me. This is average precision at different sizes. So this is for small objects, for medium objects, and for large objects. You can see how both models actually are performing worse for the small objects compared to the large objects. Mask quality rating distribution. Interesting to see John Knack from Adobe AI tweet 5 years ago I could never get at Google. I mean, what does he mean by something like this, right? Segmentation models? Like, people have been training segmentation models for fucking decades at this point. Is he referring to a segmentation model that's trained on a large amount of data? Maybe. I could see that, but I don't know if Adobe has the scale that Meta has, right? Like, the proprietary data set that Facebook has is so huge, right? They have all of Instagram and all of Facebook, which is a huge amount of data. And they also have way more money than Adobe, so I think they can train bigger models on for longer. So I don't know, maybe he's referring to the kind of like the point, or doing it from a single point, right? So this kind of like way that you kind of like click on a point like that. Maybe that's what he's referring to. But Adobe's pretty good at AI, but they're definitely existential at this point, because what is the point of Adobe Photoshop if you can just text the image, right? Who needs Photoshop if you can just describe to the computer in natural language what you want and then it creates it for you? So I think Adobe is in the hot pot right now, definitely boiling, because their entire concept of selling specialized software for creating what are effectively images, I think, is going away. Think about a 10-year timeline. Elvis dataset, but there are still idiosyncrasies. They are simple polygons. This is one thing that's really annoying about Cocoa, is that the masks are polygons. So in Cocoa, these masks are polygons, which they're not like pixel level masks, right? There's a difference between polygon versus pixel level. Polygon mask versus pixel level mask. If I can find it. Can't really find a good image, but like a polygon is something like this, right? So polygon would be the object inside these red lines, right, which are polygon. But really, what you want is pixel level mask, which is more what this like here is, right, where every single pixel is labeled as either being part of the object or not part of the object. But for a very long time, you were training these segmentation models on supervised learning with human annotated data, and annotating pixel level segmentation by hand is absolutely brutal and can take like minutes per image, versus segmenting a polygon by hand is significantly faster. So that's why Cocoa, which at this point is a little bit old, it's probably, is it 10 years old? Maybe not. It's about there. You couldn't actually do pixel level segmentation. So Cocoa is polygon masks. Finally, we consider an even high-level task, segmenting objects from free-form text. For each manually collected mask with an area larger than... There it is! There it is! You know? As soon as we saw at the beginning of this paper that they're using text and images, I was like, I bet you they're fucking using clip. And I'm going to, I brought this up yesterday, but I'm going to bring it up again. This is my, my finest meme that I've crafted. Oh no. God. That is the current state of the art of computer vision, is that everything is fucking clip. Literally, clip is carrying the entire world. Someone needs to train a better version of clip. Like, why don't we have a clip 2.0? Why don't we have a clip 3.0? Right? If every single computer vision paper is using clip, like the benefit we would get from having a better version of clip would be absolutely massive. Okay, so they basically feed the mask into clip and get an embedding, and then they compare that to the text embedding from the prompt. We can train with image embeddings, but use text embeddings for... We run the text through clip's text encoder. Yeah, you can find clip. Clip is on Hugging Face. So if you need clip, you can use it there. Actually, what happens if we, see. Zero shot image classification, cat. See how good this is. Maximize. This is a picture of Boo. Cat. Unknown error. Absolute trash. Trash. Alright, back to the paper. Give the results embedded to Sam. Sam will look at that and it'll say, hey, this text embedding from from clip is very similar to this image embedding from clip. Therefore, these two things must be the same. Zero shot. Sam can work with simple, nuanced text prompt. When Sam fails to make a correct prediction, an additional prompt can help. So, a wheel, a beaver tooth grill, a wiper plus point. Oh shit, this is powerful. You can combine them. Oh, that's pretty badass. So you can have a text and a point together. That's pretty cool. So one of the things that they had in their segment anything was, yeah, this. So like, really what Facebook is interested in, right, is a VR application. So you're wearing your VR headset and you're looking at something and you can say teapot, and you combine the point at which you're looking with the teapot. Yeah, you can see how they're setting it all up, right? It's like you can see how this model really, like, the requirements, the real-time requirements, the fact that it needs to work on a point, right? The fact that it needs to work also on text. They're building this, dude. They're really building the metaverse. They're really building kind of the foundation upon which augmented reality will exist. We perform several ablations on our 23 dataset suite with a single center point prompt. Sam is operating in a zero-shot transfer setting. Sam's performance when trained on cumulative data from the data engine stages. Each stage increases when training with all three stages. The automatic masks vastly outnumber the main masks. Okay, so basically they're doing an ablation study here, and they're going to be studying manual, semi-automatic, automatic, and automatic only. And this same idea of like, okay, if you have 1 point and you have a bunch of predicted masks for that 1 point, right? How consistent are those masks? So here they're comparing how over the course of the training, as you move from this manual training process to the semi-automatic training process to the automatic training process, your consistency in the masks you get from 1 point is increasing. All of these go up. So as you get more training images, the MIOU for the points increases also with the number of points. And then these are different model sizes. So VITB, 91 million parameters, VITH, the huge one, 636 million parameters. Surprisingly, not as much of a difference here, you know? This really isn't that much. You're talking about like 59 or 57 to 59 or something here, which is really not that much for almost like 6 times as many parameters. Which is interesting. That means you could probably use this VITB line. Pre-trained models have been adapted to downstream tasks since the early days of machine learning. This paradigm has become increasingly important in recent years with a growing emphasis on scale. Such models have been recently rebranded as foundation models. Yeah, I agree. This is kind of what we were talking about at the very beginning, that is a segmentation model that you can use for segmentation tasks. Is that really a foundation model? Like, are foundation models because they're adaptable to a wide range of downstream tasks? Or are they really foundation models because they're trained on a big data set? So I think that if your definition of foundation model is that it's a huge model trained on a huge amount of data for a huge amount of time, then yes, SAM is a foundation model. If your definition of foundation models is a general purpose model that can be used for a huge amount of downstream applications, then no, I do not think SAM is a foundation model. I think it's a segmentation model, which is already a pretty constrained task. Inherently limited scope. Yeah, they're kind of agreeing with that. Represents an important yet fractional subset of computing. Vast majority of its capabilities come from large-scale supervised training, but is using supervised training on a data set that you labeled yourself. Isn't that self-supervised training? Right? Like, there's a little bit of kind of like wordplay here where like, hey, technically we're using supervised training because we have an image and then we have like a mask and you're predicting the mask from the image. But if the mask you got for that image was the output of the model itself, I feel like that's in the same, that's self-supervised learning, right? Like, I don't know. It feels like self-supervised learning to me. It feels like calling it supervised learning is not necessarily being honest. Trained models can power new capabilities even beyond ones imagined at the moment. One prominent example is how CLIP is used as a component in larger systems such as DALL-E. Our goal is to make this kind of composition SAM. For example, MCC can easily use SAM to segment an object of interest and achieve strong generalization to unseen objects for 3D reconstruction from a single RGB image. In another example, SAM can be prompted with gaze points detected by a wearable device, enabling new applications. Yeah, this is the real interesting application for Meta here with their VR headsets. Segmentation. While SAM performs well in general, it is not perfect. It can misfind structures, hallucinate small disconnected components, and does not produce boundaries as crisply. So, I constantly use the word crispy to to describe images and the quality of masks and the quality of things. But I'm glad that I'm not alone here, and that other people in the computer vision community are now using. Of course, they don't know who the fuck I am, right? So it's not like I taught them the word crispy, but I'm glad other people are using the word crispy. We expect dedicated interactive segmentation models. SAM is designed for generality and breadth, rather than a high IOU interactive segmentation. Our foray into the text-to-mass task is exploratory and not entirely robust, although we believe it can be improved. It is unclear how to design simple prompts that implement semantic and panoptic segmentation. Finally, there are domain-specific tools such as 7 that expect outperform SAM. The Segment Anything project is an attempt to lift image segmentation into the era of foundation models. Our principal contribution are a new task, model, and dataset that make this leap possible. Whether SAM achieves the status of foundation models remains to be seen, and how it is used in the community. We expect the perspective to release over 1 billion masks and a promptable segmentation path ahead. Yeah, I think this is useful, and I think that they're correct in saying that there's a lot of use cases for segmentation models, right? Even just in the papers that we were looking at earlier in this week, right? These NERF papers. A lot of times in these NERF pipelines, you want to have masks, right? So what was the paper that we were looking at? Like a NERF paper. File. Bundle SDF. This is the one, right? So it was not a NERF, or it is a NERF paper, but in their pipeline, right, they have a segmentation model, right? So right here, object mask. You see this? So video segmentation network. They're using a segmentation model here to get the mask, and this video segmentation network here, probably not as good as this one, right? SAM, this segmentation model is probably better than whatever they were using here. So in this world of computer vision systems that are composed of multiple different models in this pipeline, if you improve any one of those models that are part of the pipeline, you improve the whole system. So if this work here, this SAM paper, results in every single future paper now using the SAM segmentation model and benefiting from that, then I think this is a huge win. And with that said, someone really needs to make a better CLIP model, because so many papers use CLIP, and if it was better, every single other paper would be better. So I appreciate Meta for making a good segmentation model that people can use for segmentation tasks in their particular work, but I really wish they would make a better CLIP model, because that to me is the biggest low-hanging fruit, is for one of these companies to train a huge CLIP model on every single piece of data that they can get their hands on. Okay, maybe scroll through the appendix here a little bit. Segment anything model, channel height width, 14 by 14s, windowed attention, 16 patches. Right, so these vision transformers, they break up the image into the patches, and then they embed each of those patches, and then you end up with a sequence of these patches, usually with an associated position embedding. Input resolution of 1024 by 1024. Image embedding is 64 by 64. To reduce the channel dimension, we use a 1x1 convolution to get 256 channels. How would you fine-tune this model if you wanted to keep prompting, e.g. with multiple points, quite flexible on a downstream task? I don't know if you want to fine-tune this. I don't even know if you can fine-tune this. Right? They don't give you, like, I was looking at this. I don't know if they give you the training script. They give you the model, but they don't the actual script. I think the way that they want you to use this is via a zero shot. So use this in a zero shot manner and see if it works on your downstream task. Downsampling the masks here. Each layer is separated by GELU activations layer norm. Here's your image embedding, 256 by 64, 64, so 64, 64 size, and then 256 channels. Here's your attention mechanism, multi-layer perceptron. Here's combining the prompt token, token to image attention, token to image attention, image to token attention. You have a different head here for different masks. We refer to these embeddings as tokens. Yeah, so in the natural language community, when you take a text and you turn it into a vector, you'll call that a token. But tokens and embeddings are basically the same thing. It's just different words for the same thing. It's like input either in text or in image modality, which has been turned into a vector that represents the content of that input. During cross attention, the image embedding is treated as a set of 64 square 256 dimensional vectors. So, I mean, attention mechanisms are very sensitive to the length of the sequence. The memory kind of explodes if you're not careful. So, feels like this is actually our memory, potentially. Positional encode embeddings are added. Which one are they using? What positional embedding are they using? Or encoding, sorry. All attention layers, 8 heads. Supervise mask prediction with a linear combination of focal loss and dice loss. 20-to-1 ratio of focal loss to dice loss. Focal loss to dice loss. So basically there's a weight. The actual final loss function is a weighted combination of these two loss functions here. And mostly it's the focal loss. This is the standard mean squared error. Boxes are taking random noise added in each coordinate to a standard deviation equal to 10%. So they kind of like shift the box around, make it a little bit bigger, a little bit smaller, to get a little bit of augmentation going on there. Find diminishing returns after 8 iteratively sampled points. Use the Atom W optimizer. Have linear learning rate warm up and then a learning rate decay schedule. The initial learning rate is 8e to the negative 4. And then by the end, it's probably way smaller. Have a weight decay. Well, they also have dropout. We distribute training across 256 GPUs. You can bet your ass those are A100s. That is monster amount of GPUs. Masks were generated from a rectangular grid. Fairness crap. Here's a description on these different data sets. The X-ray data set here. Edge detection. Look at this nice little ram with horns. Does seem to mess up this patch there. Mask. Probing the latent space of SAM. Okay, let's see. We perform an initial investigation to qualitatively probe the learned latent space of SAM. We compute mask embeddings by extracting an image embedding from SAM, image crop around the mask and its horizontally flipped version. Figure 17, we showed 3 examples of a query mask and similar masks in the same image. Observe that the nearest neighbors for each query show some, albeit imperfect, shape and semantic similarity. They indicate that the representations of SAM may also be useful for a variety of purposes such as data labeling, understanding the concepts of datasets, or as features for downstream tasks. I think for you scroll prizers, that's what you want right here. Features for downstream tasks. Quality rating. Hard. Where do the data annotators for Facebook exist? I'll tell you that. Are they also using people in third world countries? We worked with 130 annotators. The annotators were all based in Kenya. There you go. We do not believe socio-demographic characteristics of all annotators meaningfully impacted the annotated data. I don't know. I think when you use people from third world countries, they're more interested in, they just want to feed their families, you know, so they're just going to annotate as quickly as they can. But it's just weird that we live in this world where like you have people who sit there and like annotate images as a living, and it's even weirder that we outsource that to like the lowest countries that have like the cheapest labor, which is kind of dystopian. Okay, so that was segment anything. Let's look real quick here at the segment anything sites. This is something I'd like to look at. Look at the commits. Contributors. Pause. Come on, come on, come on. Crunch this data for me. Bit crunchy. Jesus. Come on, GitHub, get your shit together. Why must it be like this? There's a point cloud, so they're using segmentation to segment out the depth. I don't know what the fuck this is supposed to mean, but right. I guess we're just not gonna know sites. Another thing you can do here is look at the releases and the packages, but no releases, no packages. Apache 2. You can also go like this. GitHub star. GitHub star history. Damn. 10,000 stars. I mean, GitHub stars are a little bit sketch because you can actually purchase them. But Poison, no problem, man. Hopefully I answered your questions. And yeah, thanks for asking questions, dude. I'm definitely not annoyed by questions. I prefer when people ask questions. It makes the stream more interactive. Cool. So hope that was interesting. Thanks for hanging out. Thanks for listening. Hope you can maybe find a use for this in your projects. I'm certainly going to maybe get this working and see if I can maybe put this into the scroll prize. It's probably going to be kind of annoying to set up, though, so we'll see if I actually get anywhere or if I just end up doing something else. But cool stuff. I appreciate it. I like Facebook releasing this. Thank you, Facebook, for releasing this and releasing the code. But give us a better clip. That's what we really need, Facebook. That's what we really need. We need a better clip model. Thanks, everybody. Like, subscribe, hang out in the Discord with us. See you guys.